Okay, so while the JWST pipeline does produce standard data products such as 3D cubes for IFU observations, um, the standard 1D products aren't usually useful because they don't know where your source is in the field of view, or you may have multiple sources in the field of view. So this is an example where your data analysis merges with follows right after the pipeline. Um, and we're also going to be using the CubeViz application from JDAViz in order to visualize the data set first and do some simple spectral extractions, followed by some more sophisticated methods of spectral extraction of a point source in the notebook. Okay, so we begin with at the top of the notebook, you'll see some introductory material. We'll be using a data set that is an IFU simulation of an IFU observation of a faint quasar. And we've used the NearSpec IPS simulator that's not publicly available, but we have provided the data set here. There's a few commands, preliminaries that we want to go through. We're using NumPy, SciPy, Specutils, JDAViz, AstroPy, a bunch of different packages from the AstroPy environment. And the first cell just resizes for the notebook to the size of the window. Not really necessary for the platform, but on your own browser you might want to do that. Imports are done with the second cell. And then we've got two data sets here. I'm just going to be importing the faint quasar version because this one is useful for the optimal extraction example that I'm going to show. And then down to the fourth cell, what we have is in order to launch the CubeViz application, first you need to create an instance of it with the first command, CubeViz equals CubeViz, in parentheses, mind the caps. And then you launch the application, shift enter to run the cell. I'm going to be going through a bunch of commands in the UI, this CubeViz tool, and you might want to follow below. I've got instructions for each of the tasks we're going to go through. So there's no live coding for this portion. And so in order to load a data set, you can do that from the notebook cell. You can also do it from the GUI itself with the import command, but we don't want to have to type all that in. So we're going to go down and load the data cube with this first cell below, which is cubeviz.app load data with the file name that we specified up above. If return, there's some warnings there that will go away soon. Okay, and what you see once the data is loaded, you're going to get a bunch of green messages at the top that the various extensions have loaded, and that takes a few seconds. You can close those. Now it's done. What you'll see is there's three cube viewers. The top left one is where you see your main flux viewer. Then there's an uncertainty viewer in the top center and a data quality cube on the right. These are all cubes that you can scrub through using this slider up at the top like this. We can't see too much, so we want to go in and perhaps change the stretch a bit. This icon here that shows the three sliders, that's for changing the display values in the image viewer. So you can click on that, scroll down to where it says stretch, maybe change it to logarithmic, and then change the percentile to 99 percentile. You can also adjust the contrast a bit, bring it up a bit, and then pull the bias over the right. So bring that down, and you might start to see a faint source in there that's the faint quasar. In order to see a little bit better, you can actually scrub through the cube again, and you'll notice there's some bright pixels around here that are consistent through the slices. The next task what we're going to do is specify a extraction region around the faint quasar. Do that, click on the hammer and screwdriver icon in the top left viewer. And you can select a circular or rectangular extraction region. And you can find where that source is. It's about x equals 17, y equals 22 or so, 21. You click and pull or drag to create a moderately large spectral extraction region. You can adjust it by mousing over or move it around and redraw it. You move around until you're happy where it is, and you may have noticed that down in the spectrum viewer at the bottom, the long viewer, you'll see that the spectrum pops up. Now, the default method for collapsing the spectrum over that spatial region is the maximum pixel, but we want to go in the spectrum viewer, upper right, to the display tools. Click on that, and if you go to click on the viewer tab and change the function to the sum, you'll actually get the spectrum summed over that region in the red, and that noisy black spectrum is actually the spectrum summed over the whole data cube, which is not particularly useful. But we're going to go in, and to the layer tab, we can suppress that by clicking on the little eye next to the gray box, like that. Now, once you've done that, you might want to adjust the pan and zoom on this, and so you can again go into the tools for the spectrum viewer. And there's bidirectional zooming, or just horizontal, or just vertical. So you can click on the horizontal one and say, pick a line of interest and move it to the center. Vertical, you click and drag to pan. And then to zoom, it's typically the scroll on your mouse or on your trackpad. And a little touchy when it comes to scrolling inside the window and also zooming. So you've got to be a little bit careful with that. A little bit of zoom on the vertical axis and see it. The scroll jumped a little bit for me. Depends on your mouse a little bit. Now you can see that some spectral features that were extracted in the spatial region. This is actually broad H beta redshift of 2 for this quasar. Okay, so now you've done a simple extraction of a spectrum in CubeViz. Okay, so we've gone, I believe, through the first 2 UI tasks. One thing that we want to do now that we have that nice spectral extraction, we're going to want to compare that rough, quick extraction with the one that we do more careful in the notebook cell. So I'm going to go down to the next cell, which is exporting a region from CubeViz. There's a try except command that just in case you hadn't selected a region, it won't crash. You run that, and you see that you actually pull out an AstroPi circle pixel region centered at 17.6, 20.6, and with a radius of 4.6 for the region that I selected. And again, the next task that I wanted to do is a little bit more complicated extraction in CubeViz. It's a spatial spectral region. And so what we want to do is go to task 3 and create a second subset. In order to change between subsets, you'll see in the top left there's this red triangle that says subset 1, and that's actually the circle that we selected in the spatial region. What we want to do is create another one. We don't ruin that one. And so you want to go to select no selection, create new in the menu that pops up. And for that, I'm going to make another circular region, slightly different from the other, slightly smaller and about the same place. And you'll notice that a second spectrum pops up for the slightly different aperture in green. But if you can see, there's a second spectrum there. Next, what we want to do is we want to select a spectral subregion. In order to do that, go down to the spectrum viewer, select the tool icons, select the spectral selection region. But now it automatically jumps to a new no selection. We want to go back to that green subset 2. You click up at the top, select subset 2. There's actually, you may have noticed there's a red dot here. There's different mathematical regions that you can select, or operators you can select. If you click on that, you see that the default is replace. And so if I clicked somewhere, it would replace the region, the spatial region with a spectral region. We don't want to do that. Instead, we want to use the AND, which is the intersection that shows up when you click that. And that's the intersection between the spatial region and the spectral region that I'm going to select. So I'm going to select this H beta line here. And you'll notice that I've only got a subset now. The green is limited to that spectral region here. And so this is an intersection of a spatial and spectral region. And for example, if we wanted to do some analysis on that small region of the cube, subregion in both spatial and spectral, you can go back up to this Lego icon in the upper right, and that's where all of our analysis tools live. We had a different JWebbinar that went over some of these in more detail. You can look that up. But just for example, you can go to line analysis. You want to select in the data dropdown subset 2, which is that small green bit, and then you can automatically see some parameters that get measured for that line, including full width half max, a centroid at about 1.22 microns, and other things. So the next part is to do a more sophisticated extraction in the notebook. And what we want to do is, we already exported the region from QViz using this command. QViz app gets subsets from viewer, and I'm pulling it from the spectrum viewer in this case. Going down to the next cell that we haven't run yet, which is retrieve the subset spectrum from QViz. And the command is QViz app get data from viewer, spectrum viewer subset 1. We're also going to print out what's in there, what's in that viewer, so you can actually decide what you want to get. So you'll see below we've got the contents psi, which is the cube that we loaded in. We have subset 1 that's still there, and I had deleted some subsets, so there's subset 1 and subset 4. What we want to grab is subset 1, and that's a Spectrum 1D object that has flux and vector axis, just like. Grab that one, and we're going to compare that in the next cell to a more, like I said, more sophisticated extraction. So what we want to do, instead of having this sort of pixelated region that we selected in QViz, we're going to use a precise circular aperture that expands with wavelength to match the PSF. And so in order to do that, oh, I'm sorry, that's the following cell. Another thing that we want to do is, since there is junk at the ends of the spectrum, we want to trim it off, starting from 1 microns to 1.44. We'll do that, and at the same time, we'll slice the Spectrum 1D object to remove the edges, which there's a couple of extra spaxels at the edges. So, all right, going to the next cell. The regions we want are defined here, 1 to 1.44 microns, and trimming in X and Y. There's a convenience function on Spectrum 1D. So what I've done here is, again, load in that cube, that initial cube. So in order to actually slice this cube and trim it down, this is the command here, and we take that spectrum untrimmed that we read in, and then we apply spectral slab to it over this trim wavelengths that I specified up here. And at the same time, we can slice in X and Y, specifying the pixel ranges that we want of the cube. We'll go ahead and do that. And since we're doing that, we actually have to adjust the extraction region that we specified in QViz, because it'll shift over a bit. Running that, warnings. Here's our trim spectral axis from 1 to 1.4 microns. So what I'm trying to demonstrate here is that Spectra 1D are your friends, and you want to use them whenever you can, because you can carry along the flux and uncertainties and wave and spectral axis all at the same time, and do arithmetic with them rather than pulling things out as NumPy arrays. Okay, so to do the extractions that I was talking about, conical extraction, we've got a aperture that we specify by our cone, radius of the cone, which expands with wavelength. And then in order to do the photometry, we're actually looping through each of the slices and using the Specutils aperture photometry on a circular aperture region. And then we just append those photometric sums into a list, which we can then load into a Spectrum 1D. So Anyway, you do that by hand, and then you can shove it back into a Spectrum 1D, and then we'll plot that with this cell. So again, we've got a very noisy spectrum because I use that really large aperture. It's hard to see here, but the conical extraction we just did is in orange, and it's actually slightly noisier, even though it gets a bit more flux at the long wavelength end. And I've also plotted a representation of the RMS uncertainty that's carried along with the spectral cube. Okay, optimal extraction. The idea behind that is that you want to divide your cube by a reference star cube. And for the reference star cube, I've created a WebPSF model PSF of this data cube for NearSpec. This actually takes 10 hours to run, so if you wanted to try it on your own and change the inputs a bit, you can by uncommenting these triple quotes at the beginning and ending. But that takes about 10 hours because it's a huge data cube, and it's doing a simulation for each slice. Instead of doing that, we'll just read in our reference WebPSF with this cell. And you'll see that there's a few extensions in here. We want the detector sampled extension here, which is a cube that's 30 by 30 spatially and then 3915 in wavelength. That actually covers the full NearSpec G140H wavelength range. We're only using the short wavelength end of that, so we're going to have to trim that. All right, so we need to line up our reference PSF from WebPSF with the science data, and to do that, we're going to run the next cell, this line where I flip the PSF. And then you want to do a centroid on that using the centroid.com_com command, and I use those to determine the shifts between the science data and the reference PSF. Unfortunately, this isn't sophisticated enough, and I was finding that to get a good extraction, I actually had to shift it a little bit more manually. There's probably better algorithms for determining the centroid of a PSF that you can use and substitute in there. You can also have the option of smoothing the model PSF to match the data if you need to. It doesn't actually matter for this data set. And then finally, I'm going to just plot up what those PSFs look like. What we've got here is on the top left is the WebPSF collapsed cube showing the PSF from 1 to 1.4 microns. And then our science data cube collapsed. I just did a NumPy sum for that. And the ratio of those two actually shows that we have, the model PSF is a pretty good representation of the data. And it also gives an idea of what optimal extraction does. What we're going to do is take a signal-to-noise weighted sum over all these spaxels in order to get one spectrum that's the best extracted spectrum for a point source. A few other plots here. You see that the enclosed flux inside the IFU aperture decreases from 98% to 97% across this wavelength range. Also, there are some slight differences between the WebPSF and the science PSF that show up as residuals in these bottom right panels. And that the quality of the reference star PSF will affect the quality of your spectral extraction. If they're not right on, there can be shifts in both in level and increase in noise if they're not well matched. So then we just have one cell remaining to demonstrate the optimal extraction. Instead of pulling out these cubes and manipulating them with NumPy, we actually just divide one spectrum 1D by the other. We divide the science data by the reference PSF and WebPSF. I do some cleaning here, removal of nans and clipping. I also have to pull out the variance array into another spectrum 1D here. And the actual algorithm to the optimal extraction is simple. I have a reference to it. I horn it all. And it basically does a signal-to-noise weighted average over all the spaxels. And then we'll run this cell. And you'll see that the optimal extracted spectrum has less noise than the extraction that we did in an aperture.